we've gotten to the point where we were able to take the term 1 over y times L minus y and change it into 1 over L times the individual terms in the denominator. So what I need to do is go and borrow this equation here somewhere, right here. So you can see what we have. What we did was we took just this part, 1 over y times L minus y, and we broke it up into two parts. Now notice the numerator is multiplied by L, and the numerators here are multiplied by 1 over L. So ultimately the left-hand side just becomes 1 over y plus 1 over L minus y, because this cancels out with those. That whole thing times dy is equal to k times dt. Now at this point, now you can integrate. So we'd integrate each term. So the integral of the first term, something happened there. So the integral of the first term is just the natural log of the absolute value of y. The second term is negative the natural log of the absolute value of L minus y. And the reason that is because the negative sign here in the denominator. So if I used u substitution, where u is L minus y, when I take the derivative, I get negative y. Negative y is equal to, so that's where the negative sign comes from. And over here you just get the integral of k dt is just t plus c. So that's the solution, but you can change that. First thing you do is you combine these two terms using the properties of logarithms. So that's equal to that. We've normally gone in the opposite direction where we've broken this up, but in this case we're putting it back together. You can also get rid of the absolute value signs, because in these problems y is always positive and L minus y is also always positive. So let's go ahead and get rid of the absolute value signs. Okay. Next thing you do is you take e to the natural, so you make the left-hand side the exponent, and the same thing in the right-hand side. And I forgot my k here, so let's fix that. So there should be a k right there. Should be k. Okay, add the k back in there. Okay, so e to the natural log of y over that is going to be y over L minus y is equal to e to the kt times e to the c. So what I'm doing is I'm breaking this up like I did when I came up with the equation for exponential growth. And what we can do is we can call that e to the c some other number. We'll call it, let's call that c1 for right now. So we'll get c1 e to the kt is equal to y over L minus y. Now what are we going to do? We need to solve for y. That's what we need to do. So let's see. If you cross multiply, you get y is equal to L minus y times c1 e to the kt. You move this to the other side, so you'll get y plus y e to the kt is equal to L times C1 e to the kt. Then you factor out y, so you get y times 1 plus e to the kt is equal to L times C1 e to the kt. And then you divide both sides by that. So you'll get the numerator's L times C1 times e to the kt divided by 1 plus e to the kt. And then what we do is you multiply and divide by e to the minus kt. And I've messed up somewhere here. Where did I mess up? Oh, there's a C1 right here. Sorry. C1 right there. There's a C1 right there. So what we're actually going to do is we're going to multiply by that divided by C1. So these two cancel out with those two. So you end up with L divided by e to the minus kt over C1 plus, so this cancels out with that, this cancels out with that, so you get plus 1. So ultimately, we don't have to derive this. The ultimate expression is the population y as a function of time for logistic growth is as a function of time is equal to L over 1 plus, and instead of calling this 1 over C1, they call it B for some reason. So it's 1 plus B e to the minus kt. Okay. So what I did is I moved that first, and I changed 1 over C1 to be B. And let's just define what the terms are. So L is the carrying capacity. So that's the number of organisms that you can sustain with this particular environment. And K and B are constants determined from initial conditions and one additional data point. So it's kind of like the exponential problems that we had earlier. You know, we needed the initial conditions. You look like you're in a trance. The initial conditions, and we needed some other piece of information, usually some quantity at some period, at some point in time. So it's the same kind of deal. So it's just and if you plot this, it'll look, let me just tell you what the graph looks like when you plot it. So if you plotted population as a function of time, so this is y, this is t. What it looks like is it goes like this, and then it increases, and then it levels off. And this is L. So during the initial part Actually, it probably doesn't start at 0, so let me fix that. That's probably, it starts at some value other than 0. You have to have somebody like Adam and Eve. You have to have at least 2 people. So you've got some initial population, and initially it grows exponentially. But then when you start getting closer to the carrying capacity, the growth gets smaller, and therefore it curves back down, and ultimately you level off at some stable value, some stable point in the ecosystem. So let's just look at an example how you would do that. No physical. Yeah, this is from last year. Okay. So here's the problem. So don't try to write it all down. Let's just, as we go along, you can write it. But so you can write down the initial description. So this is a bacterial culture, but it has a maximum weight of the culture being 10 grams. So you grow it in a little petri dish or something, and you know that it can't get too big, and then at some point you start feeding it. It's kind of like my worm bin. Do you guys remember the worms from Ms. Nicholson's class? Well, we still have them. Yeah, so they're continuing on. So here's the story. So in the Explorer program, one of their topics was worms, vermicomposting. Do you remember that one too? Yeah, okay. So she stopped doing it after a while because the bin got kind of heavy, and she, for whatever reason, she didn't. So she brought them home, and I have taken over the worms. And so they're still growing. And right now they're a Rubbermaid container about this big, and there's about this much room in the top. That's my carrying capacity, because once it starts overflowing, then I'm in trouble. Martha wants to get rid of them. She's like, can't you just get rid of those? Just put them out in the garden. But it's good in the winter. You don't have to go outside when you're throwing you've got your vegetable scraps and stuff. You just throw them in the worm bin, and then they eat it. So I have a friend whose wife's just recently retired, and she's into gardening. And I said, does Pat do vermicompost? Well, she stopped doing it when she was working, and I said, oh, please take some worms. Martha's going to throw them out in the cold. So anyway, that's you can think of little vermicomposting worms from this case. Okay, so in this case we have bacterial culture. Initially weighs 1 gram. 2 hours later, the culture weighs 2 grams, and the maximum weight is 10 grams. So this is your initial condition. That'll give you one of the constant, which is B. And the second data point is this one, which gives you the constant K, and the carrying capacity is the numerator. And there's one of these on the test, so you need to know how to do these. It's pretty straightforward if you know what you're doing. So it says write a logistic equation that models the weight of the bacterial culture. So that's the most work in this thing. It's just coming up with the equation. Well, we know what the equation looks like. It's y is equal to 10 over 1 plus b e to the minus kt. So what we need to do is we need to use the fact that at t equals 0, that the amount of bacteria is 1 gram. So we go to the equation, set the left-hand side equal to 1. And when you set t equal to 0, so this is where t equals 0, you're going to have e to the minus k times 0. But of course, e to the 0 is 1. So you get 10 over 1 plus b. This goes to 1. You multiply both sides. You multiply both sides by 1 plus b. You subtract 1 from both sides, and you get 9. So b's 9. So we've got that part of the equation. So we'll use this to find b, which we did. B equals 9. Okay. The next thing is at 2 hours, we've got 2 grams. So we know that y of 2 equals 2. So that's at t equals 2. So what we have is so we take this number, that's the y value, 2 is equal to 10 divided by 1 plus, we now know b, 9 e to the minus k times the time, which is 2. Just turns out they're the same number in this case. So now you have to solve for k. So you do the same thing. You've got cross multiply, so you get 2 times 1 plus 9 e to the minus 2 times k is equal to 10. Divide both sides by 2. Then subtract 1 from both sides. Divide by 9. Then you get your calculator out, take the natural log of both sides. So you get the natural log of e to the minus 2k is equal to the natural log of 4/9. So the natural log of 4/9 is negative 0.811. And what we have over here is negative 2k. So negative 2k is equal to negative 0.811 divided by negative 2. And you get 0.405. So that gives you k. So now we can take the equation and plug in what we know. So we know y of t equals 10 divided by 1 plus 9 e to the minus 0.405 t. So that's the equation, the logistic growth equation. And just to make sure I did it right, I'm going to plug in 2 to make sure I get the right answer, or the same answer I just did, because you can always make mistakes. So if I take 10 divided by 1 plus 9 times e to the negative 0.405 times 2, I should get 2, which I get 1.999, so that's close enough. Okay, so I did it right. So that's the first part. So let's just write it down here so I'm going to, so y equals 10 over 1 plus 9 e to the minus 0.405 t. Okay. So next thing, find the culture's weight after 5 hours. So all you have to do there, once you have the equation, what is y of 5? Question mark. So all you do is you plug in t equals 5. So why don't you go ahead and do that part. Make sure you know what you're doing with your calculator. So plug in 5. And it's going to be somewhere between 2 and 5, because at 2 hours, it's 2 grams. And we know it can't get more than 10, so it's got to be somewhere between 2 and 10. So that's kind of a check of whether you are doing it correctly or not. And I'll do it on my calculator to see what I get. Actually, it's easy for me because I've already got the equation in there. Let's see what my number is here. So one of you were right. I'm not telling you which one's right. Yep. No calculator. No. Okay. You do have your calculator. You don't have your calculator. Okay. Yeah, that's the easy part. But so the answer is 4.57. So that makes sense. Okay, the next one is, when will the culture's weight reach 8 grams? So in this case, you're still using the same equation, but you're solving for t given y. So part C will be 8 equals 10 divided by 1 plus 9 e to the minus 0.405 t. Solve for t. So again, why don't you guys try that? It's basically the same way that we solve for k, except we're solving for t this way. So you can look back at your notes where we solve for k, and the only difference is you'll get to a point where you'll have negative 0.405 t is equal to something, and then you'll divide by this to find t instead of to find k. So here's an example of using solving exponential equations. When you did pre-calculus. Let's see what we got here. Let's see if Zane's got an answer yet. You can get it worse. How'd you do the last one? Oh, you had to calculate on your phone? Were you trying to do it in your head instead of writing it out? Yeah.
I was banking on a delay today. I'm not feeling it.
Oh, you're not feeling it? Okay. What'd you get?
8.8.
Yeah. Let's see what you got here. Okay, so that's right. Not sure what you did there, because that would be 1 point. Oh, I see what you got. 1.25. You're right. Yeah, 2/8. Okay, continue on. You are doing okay. Okay. Let's see. Wait for one of you guys to get it. Who's this? I think Asia's got it. So the answer is 8.85 hours. So I'm going to go through it quickly here just to. So what I did was I did 2 steps in one here at the first, which I think some of you did. So I divided by 8 and multiplied by that. And then if you subtract, then you subtract 1 from both sides. So you get, 10 divided by 8 minus 1, which is 0.25. And then you divide by 9. So you get e to the negative 0.405. T is equal to 0.0278. Take the natural log of both sides. And something's wrong. What did I do wrong? Did I do something wrong? Because that was like 3 point something. I did that earlier. Let me go back up here, see what I did wrong. No, you have to divide by 9 first. Well, apparently I did it right the first time because you guys got the same answer. So what did I? Let's try it again here. 10 divided by 8 minus 1 divided by 9. Natural log of the answer. Oh, no, that's right. So you take the natural log of 0.0278. I just took, and that is equal to negative 3.58. So you get negative 0.405. T is equal to negative 3.58. Divide by negative 0.405, and you get 8.8. Okay. The last two, I'm not going to go into a huge amount of detail. It says write the logistic differential equation. So the original differential equation was that dy dt was equal to ky times 1 minus y over L. Let me double check, make sure I did that right. So back to the original differential equation that I solved. Here it is. dy dt is ky times 1 over m. Okay, so I got that right. So all you have to do to come up with the original differential equation is to now put in the values of k that you know. This number isn't known until you apply the initial conditions, but what you would say is the differential equation is dy dt equals negative 0.405 y times 1 minus y over 10. So it's just from solving the equation, the model equation, which we knew applied, solving for b and k, and then putting them back into the differential equation that this one was based on in the original point. It says use Euler's method, but we're not going to do that. And at what time is the culture's weight increasing most rapidly? So let me Well, I drew a picture here somewhere. What this thing looks like. Where did it go? Must have. Somewhere here. There it is. Oh, got way ahead of myself there. So the slope's low here, and then it increases, and here's where it increases most rapidly, and then it levels off. Well, the way you would find the point where the function increases most rapidly is to find out where the slope is a maximum. So you'd have to take the derivative of this equation with respect to time, and then find the value of time where that where this equation has the highest slope. So you'd actually could take the second derivative and look for where the second derivative equals 0. Because you can also, this point that we're looking for where you have the maximum slope is also a point of inflection. So here it's concave up, here it's concave down. The point of maximum slope is where it changes from concave up to concave down. But I'm going to skip that as well. So I'm going to go ahead and assign the homework for this section. So it's just it's the same section. It's just four additional problems. So that's due next Thursday. Since we only have about 60% people here today, we're not going to work through problems in class. I'm just going to wait to do that tomorrow. So it's just mostly going to be lecture. So we'll get some more practice at this. It's just we're going to wait till tomorrow. So on the test, there's usually one that's exponential growth or exponential decay problem, which really has nothing to do with calculus. It's using the results of calculus. There's a logistic growth problem, again, which the equation comes from calculus, but the application is just algebra, really. So usually people do well on those two problems. So we're gonna move to the next section and cover the material. Like Zane said, he wasn't ready to come in today. He thought he wasn't. His brain was not ready for today's class. So unfortunately, your brain still may not be ready for what I'm about to show you. So we're going to derive the procedure for handling one particular kind of equations, which are fairly common. They're called first-order linear differential equations. So the first thing to do is explain what is a first-order linear differential equation. Oh, before that, though, and don't write this down, this is a table of contents from a differential equation class. This is section 6.4 is the last section that we're going to do. So we're only covering 4 sections. We're going to spend 3 weeks maybe on differential equations, but you can have a whole semester class on differential equations. And so I was just going to explain the kind of things you might have in a full differential equation class. So you've got first order equations, which first order just means it's the first derivative, which is what we've been dealing with. In calculus, we've actually dealt with second derivative equations, which is where we've took the acceleration and integrated that to find the velocity, and then we integrate that to find the position. That's a second order system. We're going to cover the third topic under first order equations, which is called integrating factors. Exact differential equations are like homogeneous equations. So that's just manipulating the equations to get it so we can separate variables. Homogeneous differential equations are kind of like the easy separation of variable problems. So we're covering a lot of the first order equations. Then they have special second order equations. Those are the easier second order equations, where the second derivative is a function of time and the first derivative, or the second derivative is a function of the first derivative and the function itself. Then you have second-order linear equations, which we haven't defined linear, but there's no squared things in there. That's there's no, everything just raised to the first power. And then you go to higher order linear differential equations. If you have a third order equation, systems of differential equations is like systems of linear equations. Systems of linear equations is you have 3 equations, 3 unknowns. When you have systems of linear equations, you have 3 unknown things, but they're in differential equations. But usually they're for first order, so they just have the first derivative. Laplace transforms are a way of solving, as the name implies, by transforming the equations. And these are really useful for engineering or physics, so that's why you take that. Series solutions. We're going to talk about series solutions in Chapter 9, but not. This is series solutions of differential equations. A little more details. So anyway, that's just some of the topics you would cover. Okay, here we go. So the definition of a first-order linear equation. So what you see, we have a dy dx plus some function p that's a function of x, which is multiplied by the variable y, and that's equal to another function q, which is a function of x. So let's look at the words and explain why the words apply to this particular equation. First order, that just means there's a single derivative. So, we can write this equation this way, or we could write it as y prime plus p of x, y equals q of x squared. If it had y double prime, it would be a second order. It had y triple prime, it'd be a third order. So that's why it's first order. Linear is because we have just y. We don't have y squared. So let me just show you what a nonlinear differential equation would look like. So if I were to have the same thing, y prime plus p of x times y squared equals q of x, that would be nonlinear. So linear means we just have y. And differential equation just means it involves a derivative. So if we had, I'll say, let's write second order. I'll write that down. I kind of mentioned it, but if we had, y double prime plus y prime plus p of x times y equals q of x, that's second order because of this thing. This is nonlinear because y is squared. Okay, so that's it for the... Now, down here I've written a specific equation that's a first order because it's just a single derivative. It's linear because I have y. And this equation is what's it called in standard form. It means that you have the y prime term first with a coefficient of 1, and then you have the y term next, and then all the other stuff is on the other side. So it fits the equation up there, and what that would allow me to do, once it's in standard form, I can identify the p of x and q of x. So I can say for this equation that p of x equals x squared and q of x equals the cosine of x. So let me just make up another differential equation. Let's say I had 2x y prime plus x cubed y is equal to e to the x. So that's another first order equation, but it's not in standard form. So the way I would, to make it into standard form, so say make into standard form by dividing by 2x. So I'm just divide everything by 2x. So I'll get y prime plus x squared over 2y is equal to e to the x divided by 2x. You can see I've canceled out one of the x's here. So that's standard form. And so I can say p of x equals x squared over 2, and q of x equals e to the x over 2x. So that's what it means. Whenever you solve these kinds of equations, if you look at them, first you have to determine if they're linear and first order. Once you do that, then you have to say, oh, I need to put it in standard form, which means getting the coefficient in front of y prime being 1. You'll see why in a minute, but just believe me. Okay, now this is the product rule. We mentioned this the other day, that we're going to use the product rule kind of in a backwards direction. So the product rule says if you take the derivative of a product of two terms, it's equal to the first term times the derivative of the second plus the derivative of the first term times the second term. And if you look at, if I look at, say, this example, I've got something prime and something not primed. So this kind of looks, the left-hand side kind of looks like the product rule on the right-hand side, except in this case, I've got G, say this is G prime of X and this is G of X. I don't have an F of X, and I don't have an F prime of X. Or I might, if this is F prime of X, maybe that's okay. So what I'm trying to do is to take this equation and fit it into looking like the right-hand side. So then I can combine the two terms. I can combine these two terms into one term, like I would do going the opposite way with the product rule. So that's the concept. Because if I say, what is the integral of d dx of f of x times g of x, that's equal to f of x times g of x. So the integral of the derivative is just that. So this integral is really easy. So if I can combine two terms like this so that they fit this, then I can combine them into one product, and then I can integrate them, and the integration's piece of cake. Okay. So here's the derivation. Don't write it down. Just try to follow along as best you can. We're going to use the results of the derivation, not the derivation itself. So at the top, you'll see that there's the differential equation in standard form. And what you're trying to do is you're trying to figure out what function can I come up with? What is the function if I multiply the original differential equation by this function such that the resulting two terms can be combined into a product? So the whole purpose of integrating factor is to figure out what this integrating factor is, so the whole thing works out. Now I'm going to remove a few things that kind of bog you down. So what I did is I took the x part, instead of u of x, I'm just calling it u. Instead of p of x, I'm calling it p. Instead of q of x, I'm calling it q. So what I'm going to do first is I'm going to multiply this function that I don't know what it is yet, and I'm going to distribute that to each term in the original differential equation. So I'll get u times y prime, u times p times y is equal to u times q. Okay. So how do we choose u? Well, we choose u such that the product rule works, such that u times y quantity prime is So that's the product rule. The derivative of a product is the first term times the derivative of the second plus the first derivative of the first times the second. So how do we get that to work? Well, you can see that what has to happen is that we're back over here. Let's come down to here. Like I said, this part's okay. I've got a prime part and a y part. What has to happen is that this here has to be the derivative of that. So if this is f of x, then this has to be f prime of x. This is g prime of x, this is g of x. So the requirement is if u prime equals p times u, then you've chosen the correct u. So what we do is we solve this differential equation, this little tiny differential equation for u, and then we use that u in the bigger differential equation. Okay, so let's go to the next page. So that's how we choose u. Okay, we choose u such that this is true, and I didn't go anywhere yet. Okay, now I'm going to put the. So this is this equation. I've just made it bigger again. So this is a differential equation in terms of u. So I rewrite u prime of x as du dx. Then I separate variables. So I take u of x and move it over to the left-hand side, and I take dx and move it to the right-hand side. So I'm separating the variables. I integrate both sides. So the integral of du over u, we all want to know what that is, the natural log of u. And the right-hand side is just the integral of p of x dx. So this integral depends upon what this constant is, or not this constant, but this term in the original differential equation. So left-hand side is the natural log of u, right-hand side is the integral of p of x dx. So if you take e to the natural log of u and e to this side, you get u is equal to e to the integral p of x dx. And we don't need an arbitrary constant. When we integrate this, or when we integrated this, we don't need an arbitrary constant because we just need one solution that works, and the solution with c equals 0 is as good as any. So we never add an arbitrary constant. We just integrate it. Both when we did this integration and when we do this integration, we leave out the arbitrary constant, as you'll see. So that's how you come up with the integrating factor. So the best way to do this is just to show you how it works. So here's our initial differential equation. X cubed y prime plus xy is equal to e to the x plus 1. So the first thing you have to do is you have to put it in standard form. So standard form has y prime by itself. So we're going to divide every term by y cubed. So if you do that, you'll get y prime plus x divided by x cubed times y is equal to e to the, well actually what we're doing here is says determine whether the differential equation is linear, manipulated into standard form. So let's skip that one, to be honest. We'll come back to it. I'm trying to find the equation that we can use there we go. Okay, let's do it here. So we're going to use the integrating factor method here. Solve dy dx plus 2 over xy is equal to 3x plus 2. I'm going to rewrite dy dx as y prime. Okay, it is in standard form already. If it wasn't in standard form, we would do. So standard form, check. Identify p of x. Well, p of x is just the term in front of y. So p of x equals 2 over x. So that's what I'm doing here. Once I put it in standard form, I can identify what p of x is. The next thing you do is you calculate the integrating factor. So the integrating factor, which we use u, is equal to e to the integral of p of x dx. So that's just the definition. Once we identify p of x, we can put that into our integral. So we get 2 over x dx. And then we integrate this thing. So you get e. I'm going to factor out the 2, so you're going to have the integral of 1 over x dx. Well, the integral of 1 over x dx is the natural log of x. It's actually the absolute value of x. Now, earlier I said we don't add the arbitrary constant when we're doing this procedure. So notice I don't add c. I let c equal 0. You could let c be anything, and it would give you the right answer, but in this case, we're just going to leave c equals 0. Now, I can't use the inverse properties of logarithms and exponentials because this 2 is outside the logarithm. So what I'm going to do is I'm going to use the properties of logarithms to move the 2 inside the logarithm. And so what that term becomes is e to the natural log of the absolute value of x quantity squared. So this factor out front becomes the exponent. Now I can use the inverse properties of logarithms and exponents. So e to the natural log of x squared is going to be e to the natural log of x squared. I can get rid of the absolute value sign because once you square it, it doesn't matter whether it's positive or negative anyway. So this is my integrating factor. Now, once I have found my integrating factor, I take my original differential equation, which is up here. So let me write this down before we move along. So I take my original differential equation, and I multiply it by the integrating factor. So let's distribute that. So you get x squared y prime plus 2x squared divided by x times y is equal to 3x cubed plus 2x. But I can simplify this by canceling out one of the x's there. Okay, so all I've done is multiplied the differential equation by the same term, and yes?
That last term should be 2x.
Squared, yes, thank you. 2x squared, get rid of that, okay. So I haven't changed anything, I've just multiplied by the same quantity. That's what we've been doing since algebra from day one. But the key thing to now notice is that the derivative of x squared is 2x, and the derivative of y is y prime. So now I've got it in a form where it fits the product rule, and you can combine those two terms into one term. So it becomes x squared y prime. So the right-hand side, left-hand side collapses into a single term. So let me just prove that that's true, and we'll go back the other direction. If I said, what's the derivative with respect to x of x squared times y. So what you do is you take the first term times the derivative of the second. You'd be using implicit differentiation, so you get the derivative of y would be 1, but you multiply by y prime. And then you take the second term is going to be the derivative of the first term times the second term. So what I get is x squared y prime plus 2xy, which is exactly what I had here. So it does work. So this whole concept of integrating factor is to combine these two terms into one single term. And then what you can do is if you multiply both sides by dx and integrate them, like that, when you integrate this thing, it just becomes the term in the parentheses. So that integral is a piece of cake. And the right-hand side, we just use our normal integration rules. So we're going to add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent. This is where the arbitrary constant comes into play. So we finally do have an arbitrary constant, but that took a while. And now all we have to do now, all we have left to do is solve for y, and we've solved the equation, which we will do tomorrow. So it's the whole idea of integrating factor is to take a first order linear differential equation and make it so that the left-hand side can be combined into one term, and then you integrate that one term, and it's a piece of cake. So, Jacob, I had time to do the calculus ones. I haven't done the physics ones, but I can do it. Are you going to be around for a while, or are you leaving? Probably about 20 minutes. Okay. Well, what I'll do is I can't get everything on there because so I can do chapter 15 and 16 or something, and then